Okay, so section 7.1 is on inverse trigonometric functions. So first up, let's talk about this word inverse. So in Math 126, we learned about inverse functions in chapter 5. I think it was section 5.2. So here I'm going to write recall, and I want to just give you a brief recollection of what an inverse function is. So recall for Math 126, if f is a one-to-one function, then there exists an inverse function of f. And it's denoted f inverse. And that inverse function is the correspondence from the range back to the domain. Okay, so if f is a one-to-one function, then there exists an inverse function of f, denoted f inverse, which is the correspondence from the range back to the domain. Okay, so easy inverse functions we've seen before in our math career are things that do the mathematical opposite operation. So multiplying by 2, the inverse would be dividing by 2. Adding 5, the inverse would be subtracting 5. So these are things that do the opposite mathematical operation. So the important part here is that in order for a function to have an inverse, it has to be a one-to-one function. So let's refresh our memory on what this means. So a function means each x has only one associated y. And then if a function is a one-to-one function, that means each x has its own unique y, meaning that each y only has one x that maps to that y. Okay, so in order for a function to exist, or an inverse function to exist, the function has to be one-to-one. So let's look at some really easy examples of inverse functions, and then we'll apply this to our trig functions. So here's a function f. I have a list of people and their ages. So I have Bob, Tom, Sally, Mary, and ages I have 22, 24, 26, 28. So Bob's 22, Tom's 24, Sally's 26, Mary's 28. Okay, so the first question is, yes, this is a function. Now our next question is this a one-to-one function? So in order for it to be a one-to-one function, each x can only, in order to be a function, each x can only be associated with one y. In order for it to be one-to-one, each y can only have one x that maps to it. So what we want to make sure is that none of these x values, none of our inputs share the same y, and they don't. So that means this is one-to-one, so that means the inverse exists. I don't know if these are our students or not. Off-road and legend to us. Well, we'll see. We'll see what happens. These ones aren't muted. Muted, okay. Okay. Okay, so let's write out our inverse function. So our inverse function does the exact mathematical opposite. So we're going to go from age to people. So in ages, I have 22, 24, 26, 28, and these are going to map to people. Bob, Tom, Sally, and Mary. Okay, so it is the exact opposite. Let's look at one more. We have a function f of x, which is 2x plus 1. Some points on this function, if I plug in x is 0, y would be 1. If I plug in x is 1, y is 3. And if I plug in x is 2, y is 5. Those are some points. If we look at the inverse function, which does the mathematical opposite, it's 1/2 x minus 1/2. Some points on this would have x and y reversed. So we'd have 1, 0, we'd have 3, 1, and we'd have 5, 2. And I'll put dot, 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 because those are just some points. So what you can see, the difference between a function and its inverse is that the roles of x and y have just flip-flopped. Okay, so a function takes x and maps to y, the inverse takes y and goes back to x. The other thing you will have noticed, hopefully, or remembered from Math 126, is that the domain of a function is equal to the range, the output, the y values of the inverse. And the range of a function is equal to the domain of the inverse. So this is true because just the roles of x and y have flip-flopped. So the domain and range switch places. Okay, now in order for a function to have an inverse, a function has to be 1-to-1, which means that each y can only have one x that maps to it. Now let's just think briefly about our graph of sine, which we know looks something like this. Right, and if we think about our graph of sine, in order to determine if a function is 1-to-1, we had a visual test. Do you guys remember what our test was to decide if a function was 1-to-1, what the test was called? Shout it out, anyone remember? Okay, so close. So vertical line test tests if something is a function. Okay, so vertical line test tests if something is a function. So if, and let's see, someone at home got it, horizontal line test, yes. Okay, so vertical line test tests if it's a function. This checks that each x only has one y. In order for it to be 1-to-1, what we do is check a horizontal line test. So the horizontal line test checks that each y only has one x that maps to it. Now, if we look at this specific y value has an infinite number of x's that map to that y value. So that means sine is not 1-to-1. Cosine also not 1-to-1, tangent also not 1-to-1. So if we run any of a horizontal line through any of our trig graphs, it's going to cross in an infinite number of points and not 1-to-1. Now you might be thinking, Adrian, why do we have this whole section on 1-to-1 functions and inverse trig functions if sine, cosine, and tangent are not 1-to-1? So what our goal is to define an inverse. But in order to do that, we have to force this to be 1-to-1. Okay, so sine, cosine, and tangent, and of course the reciprocals the reciprocal functions as well, are not 1-to-1 functions. However, we want to define an inverse. So what we're going to do is we are going to place restrictions on the domains to force them to be 1-to-1. Okay, so sine, cosine, and tangent are not 1-to-1 functions, but we want to define inverse functions. So we're going to place restrictions on the domains to force them to be 1 to define the inverses. Now, big picture, why is this important? Big picture, why is this important? Because what we've done in the last chapter is our input was an angle. So we found sine of 45. You can apply this to real world engineering problems. But in the real world, it's easier to measure the sides. And so if we knew the ratio of sides, the question would be, what angle has this ratio of sides. Okay, so these inverse functions are going to be particularly useful in real world problems. All right, anybody need more time on this page? Okay, so what we're going to do is we're going to do this kind of the long way. We'll look at sine, we'll look at cosine, we'll look at tangent, we'll look at all three of these separately, and we're going to place restrictions on the domains, and then we'll define the inverse function, and then we'll do a bunch of problems using the inverse functions. Okay, so first thing I'm going to do is put up my graph of sine, and again, this is kind of the long way, the derivation of the inverse. But again, I feel it's really important at this level of math that instead of me just telling you all this stuff, that you understand where it comes from. Because students all the time ask me, why do we have these crazy restrictions? And it's because we need to force it to be one-to-one. Okay, so I want you to see where this comes from. So first thing I'm going to do is put up my graph of y is equal to sine of x. We know from the last chapter, our quadrantal angles give us these key points. And we know our graph looks something like this. Okay, so horizontal line test. This obviously fails the horizontal line test, right? If you run a horizontal line, it crosses it at more than 1 point, so it's not one-to-one. Okay, so what our goal is to place a restriction on the domain. The domain refers to the x values. So what we want to do is look at only a certain portion of our x values, and we want to find a portion of our x values that does two things. First, we want it to be one-to-one, which means it has to pass the horizontal line test. The second thing we want is we want it to hit all of our outputs. So we want it to hit everything from -1 to 1. Okay, so I want you guys to think about this for a second, and then we'll talk about what our range is, or I'm sorry, what our restriction on our domain is. Okay, so the other thing we like is we like it to be somewhere close to 0. Okay, so what I want you to think about is on your graph, what region of this graph can I pick so that it passes the horizontal line test, meaning it's only one-to-one, and it hits all of the values, all the y values from -1 to 1. What do you guys think? And it has to be close to 0. Where should I start and where should I stop? What do you guys think? Yep. Yep. Okay, and somebody got it at home too in the chat. Yep, nailed it. Good job. Okay, so it turns out if we look at this portion of the graph, perfect. This portion of the graph, and it looks like my yellow is not showing up very well, so let me move to pink. This portion of the graph is one-to-one. It passes the horizontal line test. Its range, the y values that we actually hit, is everything in our range from -1 to 1, and it's close to 0, so we like that. So if we restrict our domain from -π/2 to +π/2, this is one-to-one. Now realize this is not the only way of doing this. There's an infinite number of ways we could do this. We could also pick from we could pick from π/2 to 3π/2. That would also be one-to-one and onto the range. But what we like to do is pick the values that are closest to 0. Okay, so this is our convention. Okay, so now what we're doing is ignoring the rest of this graph, and we're only looking at this part. So because it's one-to-one, we can define the inverse function. So the inverse sine function is defined as y is equal to inverse sine of x. Remember that -1 up there in the superscript is not an exponent. This means inverse, so this is not an exponent. So y is inverse sine of x. This means x is equal to sine of y. Now, the domain of this inverse function and the range of the inverse function are exactly opposite of the domain and range up here. Okay, so the domain here comes from this range, and the range here comes from this domain. And we'll do tons of examples this chapter about, using these, so you'll feel a lot better about these, I promise, in a couple of lectures. Okay, so what this means in words, we have y is inverse sine of x. That's our inverse function. In words, this says y is the angle in our restriction, which is negative pi over 2 to positive pi over 2, whose sine equals x. Okay, so this inverse sine does exactly the opposite of regular sine. So in sine, our input was an angle, right? Our input was an angle, and we outputted a number between -1 and 1. The inverse, our input is a number between -1 and 1, and our output is an angle. So for example, we know from last chapter that sine of 45 is root 2 over 2. That means that inverse sine of root 2 over 2 is equal to 45. It does the opposite operation. The important thing to note here is that inverse sine can only output an angle in negative pi over 2 to positive pi over 2. Okay, so that's really, really, really important. Inverse sine can only output an angle in negative pi over 2 to positive pi over 2. So let's draw a picture of what angles it can output. So if we're looking at angles in standard position, negative pi over 2 would be down here. Pi over 2 is up here. So that means that inverse sine can only return an angle in between negative pi over 2 and positive pi over 2, which is quadrant 1 and quadrant 4. That's a Q. Okay, so inverse sine can only output an angle in quadrant 1 or quadrant 4. Furthermore, because it's between negative pi over 2 and positive pi over 2, anytime an angle is in quadrant 4, this is going to be a negative angle because of this definition. Okay, so whenever we have an angle in quadrant 4, we always ask ourselves, are we measuring positive or negative angle? It's going to be a negative angle. It has to be between negative pi over 2 and positive pi over 2. Any questions so far? And I understand that once we do some problems, this will make a lot more sense. This is just kind of the introduction and the mathematical explanation here. Any questions so far? Okay, so now what we're going to do exactly the same thing for cosine and exactly the same thing for tangent. We will not define inverse secant, inverse cosecant, or inverse tangent. Those are not commonly used. And then once we get these all defined, we'll do some problems using them, and you'll see how they work. Okay, so we'll do the same thing. I'm going to put up my graph of cosine, and then we're going to pick a restriction on our domain that forces this to be 1 to 1. So again, we know cosine has y values from -1 to 1. And here we put our quadrantal angles. That's where these key points come from. Okay, we know our pattern from cosines is 0. I'm sorry. At 0, it's at 1. Then pi over 2 is at 0. Then -1, then 0, then 1. Okay, so again, this is not 1 to 1. If we run a horizontal line through this picture, it crosses in an infinite number of places. So what we want to do is we want to place a restriction on the domain. So we want to pick a section of x values that is 1 to 1 and is onto. Onto means hit all of our values of our range. Okay. So what I want you guys to do is think about this, and then I'll ask you what our domain should be. I want you, and we want it to be close to 0, right? We want to pick the easiest one possible, even though there's an infinite number of ways to do this. We want to pick the easiest one. So on sine, we picked from negative pi over 2 to positive pi over 2. That obviously does not work for cosine, so it's going to be a little bit different. So I want you to think about what region of this graph should we take so that it's 1 to 1 and hits all of our values in our range. We usually like values close to 0, and we usually prefer positive numbers to negative numbers. What do you guys think? What should I restrict the domain to? Where to where?
0 to pi.
0 to pi, great. This one's a little bit easier to see, 0 to pi, great. So if we look at this part of the graph, x values between 0 and pi, that is 1 to 1, and it hits all of the values in the range. Now again, this is not the only way of doing it. We could pick from negative pi to 0, we could pick from pi to 2 pi, we could pick from 2 pi to 3 pi, but our mathematical convention is we use 0 to pi because we like positive numbers and we like values at 0. Okay, so let's define our inverse cosine function now. Okay, so y is equal to inverse cosine of x means x is equal to cosine of y. The domain and the range of our inverse cosine function are the domain and range of our restricted cosine function flip-flopped. So our domain here, what we input is -1 to 1, and our range, our output is 0 to pi. Okay, so these are just exactly flip-flopped from the original function. Okay, so in words, if we have y is equal to inverse cosine of x, this is saying y is the angle in our restriction, which is 0 to pi, whose cosine equals x. Now, the whole reason why we need that restriction is because otherwise we'd have an infinite number of angles whose cosine was x. Okay, so this guarantees we only have one output, which means it's still a function. All right, so the important part here is that inverse cosine can only output an angle in 0 to pi, which is different than sine. So let's take a look at a picture of this. Here's 0, here's pi. We are saying that inverse cosine has to return an angle between 0 and pi. That's quadrant 1 and quadrant 2. Okay, so this is different than inverse cosine. Inverse cosine return an angle in quadrant 1 or quadrant 4. And as we're going through examples, we'll see how this plays out. Any questions so far? Okay, so we're going to do one more. We'll do exactly the same thing to define inverse tangent. We'll look at the graph of tangent. We'll pick a restriction on the domain. And then once we get that all formally written down, we'll start working through some problems. Any questions? Okay. Okay, so let's quickly put up our graph of tangents. And this one's even the easiest one yet to see what our restriction on our domain should be. Okay, so there's a quick sketch of our graph of tangent. So what we want to do is pick a restriction on our domain. So pick some x values so that our range is our range of our normal graph, which is all real numbers, or from -infinity to +infinity. Okay, so this one should be really, really obvious. I should pick from where to where? Yeah, -pi/2 to +pi/2. So if we just look at this portion of the graph, that is 1 to 1. It passes the horizontal line test and it hits our range, which is all real numbers. So we're just going to take this part. Now, the one thing you want to be careful about here is, remember, anytime we list something in interval notation, on the outside, we either put parentheses or brackets. Brackets means we include the endpoints. Parentheses means we don't. So over here, this range, this has parentheses. This means we don't include the endpoints. And that's because infinity is a theoretical number, right? We can't actually count all the way out to infinity. So infinity always gets parentheses. This has to have parentheses and not brackets, unlike the last two examples. And that is because tangent is not defined at -pi/2, and it's also not defined at pi/2. So because tangent is not defined at these points, we cannot include those in our domain. Okay, so let's list this out now. Inverse tangent function. So y is equal to inverse tangent of x means x is equal to tangent of y. Our domain and our range for this inverse function are exactly opposite of what we found up here. So our domain is -infinity to +infinity, or all real numbers. Our range, the set of our outputs, the y values this can actually hit, is from -pi/2 to +pi/2, not including those endpoints. In words, if we have y is equal to inverse tangent of x, this says y is the angle in our restricted range, which was from -pi/2 to +pi/2, whose tangent equals x. The important part here, let me move these for a second, is that inverse tangents can only output an angle in -pi/2 to +pi/2. So again, looking at a picture of this, here's -pi/2, here's +pi/2. Inverse tangent has to return something in between -pi/2 and +pi/2, so that's quadrant 1 and quadrant 4. All right, any questions so far? Okay, so how do you remember all this? I'll show you an easy way to remember. What we want to be careful with on these inverse functions is what are allowed ranges, where we can output an angle. And again, these restrictions on the range forces it to be 1 to 1, which means we only get one answer. If we didn't have these restrictions, we'd have infinite answers. Okay, so I'll show you a picture of an easy way to remember where these restrictions are, and then we'll start working through some problems and we'll see how this applies. Anybody need more time on this page? Okay. And then I find on exam 2, the very first thing most students do when they get their exam, I see it up by their name on page 1, is draw this picture. So if this helps you, awesome. So these are angles in standard position, 0, pi/2 pi, and in the negative direction, here's -pi/2. So the first thing we figured out is that inverse sine returns an angle between -pi/2 and +pi/2. So right here, we'll just write inverse sine, however you want to put that inverse on it, something like that. The next thing we figured out was inverse cosine could only return an angle between 0 and pi. So that's quadrant 1 and quadrant 2. So here's inverse cosine. The next thing we figured out is that inverse tangent can only return something between negative pi over 2 and positive pi over 2. So that's quadrant 1 and quadrant 4. So again, inverse sine and inverse tangent will return an angle in quadrant 1 or quadrant 4. Inverse cosine has to return an angle in quadrant 1 or quadrant 2. Now, why the difference? The difference comes from the way we restricted those x values on our original graphs. Okay, so the other important thing to remember is inverse sine and inverse tangent return an angle between negative pi over 2 and positive pi over 2. So anytime we're in quadrant 4 here, this is a negative angle. So it's always going to be a negative angle in quadrant 4 based on this definition. Anytime we have an angle in quadrant 1 or quadrant 2, those will be positive angles measured in the positive direction because it has to be between 0 and pi over 2 or 0 and positive pi. All right, so there's a nice little shortcut. If you like it, cool. If not, that's okay. So let's see how these inverse functions actually work. So very first example here, we are asked to find the value. Again, on your homework, you might see some different wording. You might see the word evaluate. That still means find the value. So we'll do like 6 or 8 of these. So first one, let's find the value of inverse sine of 1. So for this section today, I'm going to write out every single problem the very long way. As you get more comfortable with these, you don't have to write them out the long way every single time. So anytime you see inverse sine, inverse cosine, inverse tangent, the first thing you should think is my output needs to be an angle. Okay, so this is the opposite of what we did in the last chapter. In the last chapter, we took sine, cosine, and tangent, and our input was an angle. So sine of 45, cosine of 30, etc. We're doing the opposite. So our output always needs to be an angle. Anytime you see inverse sine, inverse cosine, inverse tangent, the first thing you should think is you need to find an angle. Our output needs to be an angle. The second thing you should think is where does that angle need to be? Because we're looking at inverse sine, our output for inverse sine is between negative pi over 2 and positive pi over 2. Okay, so I need to find an angle in my restricted range whose sine is, and then sine has to be equal to whatever this value is. So sine has to be 1. Okay, so this inverse sine of 1, this is literally asking us to find an angle in our restriction, which is negative pi over 2 to positive pi over 2, whose sine is 1. Okay, so let's draw a picture. We are looking for an angle in between negative pi over 2 and positive pi over 2, so it has to be in quadrant 1 or quadrant 4, whose sine is positive 1. The first thing we should determine is what quadrant that angle is in. If sine is positive, should my angle be in quadrant 1 or quadrant 4? Where is sine positive, quadrant 1 or quadrant 4? Quadrant 1. Okay, so first thing we know is it has to be in quadrant 1. Okay, we're looking for an angle in quadrant 1 whose sine is positive 1. Now, anytime sine is 0, 1, or negative 1, that corresponds to a quadrantal angle. So let's take a look at our two quadrantal angles that are here in quadrant 1. Here we know this x coordinate is 1, y is 0. Here x is 0, y is 1. Remember, these go in alphabetical order: cosine, sine, cosine, sine. We are looking for the angle whose sine is 1. Sine is 1. What angle has sine equal to 1? What's the angle here? 90 degrees? Okay, so 90 degrees has sine equal to 1. Typically on your homework in this chapter, you'll be asked to give your answer in terms of radians. Okay, so this is saying, if we look at this the opposite way. So for example, we say 3 squared is 9. We could check the square root of 9 is 3. So if we wanted to check this, we could check that sine of pi over 2 is equal to 1. And yes, this is correct. Okay, so inverse sine of 1 is equal to, our answer here would be pi over 2 or 90 degrees. Again, just make sure you pay attention on the homework. In most cases, they ask you to give your answer in radians. Any questions on this? Well, let's do some more. Okay, next one, inverse sine of -1/2. Okay, so again, I'll do this the long way for you today. Anytime you see inverse sine, inverse cosine, inverse tangent, the very first thing you should think is I need to find an angle. I need to find an angle. The next thing you should ask yourself is, where does that angle have to be? We are working with inverse sine. So our restriction for inverse sine was that that angle has to be between -pi/2 and +pi/2. So we need to find an angle in our restricted range. And what do we know about that angle? We know that sine is -1/2. Okay, so inverse sine of -1/2 literally asks us to find an angle in -pi/2 to +pi/2 whose sine is -1/2. Okay, let's draw a picture. -pi/2 to +pi/2 means our angle has to be in either quadrant 1 or quadrant 4. The next thing we want to do is determine what quadrant our angle is in. So to determine what quadrant the angle is in, we look at this number. This positive or negative value tells us what quadrant we're in. Okay, so we want to find an angle whose sine is negative. Sine is negative. If sine is negative, should that angle be in quadrant 1 or quadrant 4? Which one? 4. So remember, all students take calculus. That tells us sine is negative in the 4th quadrant. The shortcut here is to remember that because we're only considering these 3 quadrants, if our value is positive, we'll be in 1. If it's negative, we'll be in 2 or 4. Okay, so it's only positive in quadrant 1, 2 and 4 would be negative. So 4 negative for inverse sine and inverse tangent, 2 would be if cosine was negative. Okay, so now we need to find an angle whose sine is -1/2. So the angle has to be somewhere here in quadrant 4. So we're doing these problems in reverse from last chapter. So we want to find this angle theta. We want to figure out what this is. And what do we know about this angle? We know that sine is -1/2. So remember, SOHCAHTOA tells us sine is opposite over hypotenuse. Our goal is to find this angle theta. Now, spoiler alert, we still only know 2 triangles. We still only know that 45, 45, 90 and the 30, 60, 90. So using the Pythagorean theorem or recognizing this, we can figure out that this third side is √3. So now our question is, what angle here has the side across from it that's the 1? Is this 30 or 60? Which one? 30. Okay, so in a 30, 60, 90 triangle, this is 30. Now, the one kicker on your answer here is that anytime we have an angle in quadrant 4 on these inverse sine or inverse tangent problems, we are measuring in the negative direction. So this angle is going to be -30 degrees. And on your homework, they always ask you to answer in radians. So in radians, our final answer here is going to be -pi/6. Okay, so inverse sine of -1/2 is -pi/6. If we do this in the reverse, we could check that sine of -pi/6 is -1/2. We could check that. It's like saying 3 squared is 9. Okay, square root of 9 is 3. We're doing the inverse operation. So if you want, you can check that. Any questions on this one? Okay, we'll keep doing some more. Okay, so next one, I have inverse tangent of square root of 3. Okay, so again, we'll write this out the long way. Anytime we see inverse sine, inverse cosine, inverse tangent, our output is always an angle. So anytime you see an inverse trig function, you should think, I need to find an angle. And I keep writing and, it should be the, there's only one angle. So find the only angle, there should only be one. Find the angle in our restriction for inverse tangent. So our range for inverse tangent was negative pi over 2 to positive pi over 2 with those parentheses. Remember, it was undefined at those endpoints. What do we know about that angle? We know that tangent is root 3. Okay, so let's draw a picture. We have to find the angle in between negative pi over 2 and positive pi over 2. So that's quadrant 1 and quadrant 4, whose tangent is root 3. The next thing we should determine is what quadrant this angle is going to be in, 1 or 4. The way we determine what quadrant the angle is in is based on this number being positive or negative. Here we're looking for an angle whose tangent is positive. So if tangent is positive, what quadrant should I draw my angle in, 1 or 4? Where's tangent positive, quadrant 1 or quadrant 4? 1, good. Okay, so I'm going to draw my angle in quadrant 1. Okay, so this plus or minus value determines the quadrant. Okay, now we're doing the problems from the last chapter in reverse. So we form our triangle. Now we know that tangent is root 3. Now the trick here is to remember these sine, cosine, and tangent, usually we see them as fractions, right? Tangent is opposite over adjacent. So the trick here is to make sure we write this as a ratio, as a fraction. So instead of just root 3, I'm going to write this as root 3 over 1. And remember that this is SOHCAHTOA. So that means the opposite is root 3, the adjacent is 1, and what I want to do is find this angle theta. Now again, we only have 2 triangles that we know how to do by hand, the 30, 60, 90 or the 45, 45, 90. So you should recognize one of those 2 triangles. If not, you could use Pythagorean theorem, find the third side, then hopefully you would recognize it. Okay, so we're looking for this angle theta, which the side across from it is root 3. So what is this angle? Is this the 30 or the 60? Which one? The 60, good. So this is the 60 degrees. Usually we answer in terms of radians, so this is pi over 3. If you want to check, you can check that tangent of pi over 3 is indeed root 3. You can check that on your own if you'd like. So here's our answer, pi over 3. Any questions on this? Okay, let's do a couple more. And this one's a little bit trickier. Okay, next one, I have inverse cosine of negative root 2 over 2. So again, we'll write this out the long way for this section. Anytime you see inverse sine, inverse cosine, inverse tangent, the first thing you need to think is I should find the angle, right? My output has to be an angle. This is opposite of what we did in the last chapter. My output has to be an angle. The next thing you should ask yourself is where does that angle need to be? It needs to be in our restriction for that inverse trig function, the range here. So help me out with this one. What's our range for inverse cosine? We have to find an angle in between what to what? What was our range for inverse cosine? Look back through your notes if you don't remember. 0 to pi. Okay, so inverse sine and inverse tangent, we're looking in 1 and 4. inverse cosine here, we're looking in quadrants 1 and 2. So what do we know about that angle? We know that cosine is negative root 2 over 2. So let's draw a picture. We are looking for an angle between 0 and pi. So it has to be in quadrant 1 or quadrant 2. The way we determine what quadrant that angle is in is based on this number being positive or negative. So right up here, I have plus or minus determines the quadrant. So we look at this value, we're looking for an angle whose cosine is negative. Cosine is negative. So what quadrant should that angle be in? If cosine is negative in which one? Quadrant 1 or quadrant 2? Which one? Quadrant 2. Okay, so I'm going to draw my angle in quadrant 2. We're doing these problems in reverse from last chapter. So I'm going to draw my perpendicular and form a triangle. Now we know that cosine is negative root 2 over 2. The trick here is to recognize when we rationalize the denominator that this is equivalent to 1 over root 2. Okay, so some of these tricks you should use, like in this last example, rewrote root 3 as root 3 over 1. That was helpful. Another trick here is to go backwards on rationalizing the denominator. This is just something you have to recognize. From last chapter, we did all of these 1s over root 2s. That's equivalent to root 2 over 2. Okay, so cosine is adjacent over hypotenuse. So that means our adjacent here is negative 1. Hypotenuse is root 2. And you don't have to write this negative if you don't want to. Remember, it's negative in quadrant 2. Okay, so we recognize this as a 45, 45, 90 triangle, which means that this angle in here is what? What's this reference angle in here? 45. Okay, good. Now, these cosine problems are a little bit trickier. We got 45. This is not our answer. Our answer is the angle in standard position. So in standard position, we start measuring from the positive x-axis and we measure out to this terminal ray. This angle is our answer. This angle is just the reference angle inside our reference triangle that gave us this. Okay, so your answer should always be the angle in standard position measured from that positive x-axis. Now, you can do this in terms of degrees or radians, but our final answer needs to be in radians for this whole section, I believe. So let's do it in radians. 45 degrees is pi over 4. Okay, so what we know, this 180 is 1 whole pi. We are pi over 4 away from being to 1 whole pi, right? So either this angle plus this equals 1 whole pi, or you can think pi minus pi over 4 gives us this. Either way, this is equal to, what's the green angle? 3 pi over 4, good. Okay, so you can either think pi minus pi over 4 gives you 3 pi over 4, or you can ask yourself pi over 4 plus what makes 1 whole pi. In the second quadrant, this angle is always going to be pi minus that reference angle, always. Okay, so if you want to check this, you can check that cosine of 3 pi over 4 is equal to negative root 2 over 2. You can check that yourself. This is our answer. Any questions on this? Okay, let's do another one. Let's do inverse cosine of negative root 3 over 2. Okay, so again, anytime you see inverse sine, inverse cosine, inverse tangent, you should think that your output should be an angle. So I need to find the angle in my restriction for cosine, which is 0 to pi. And what do we know about that angle? We know that cosine is negative root 3 over 2. Okay, the next thing we should do is figure out what quadrant that angle has to be in. We need to draw a picture. So our angle has to be between 0 and pi. We are looking for an angle whose cosine is negative. Cosine is negative, you guys just told me, in the second quadrant. So again, this positive or negative value tells us what quadrant our angle is in. Okay, so we're doing these problems in reverse from the last chapter. So we drop our perpendicular, forming a triangle. We know that cosine is negative root 3 over 2. We think so toa. So that's adjacent over hypotenuse. So adjacent here is root 3 and hypotenuse is 2. Okay, we should recognize this as a 30, 60, 90 triangle, or using Pythagorean theorem, you can get that third side there. Again, we only know 2 triangles, so you should always end up with a 30, 60, 90 or 45, 45, 90. All right, our goal is to figure out what this reference angle is. So what is the angle whose side across from it is 1? Is this the 30 or the 60? Which one? The 30, good. So this is the 30. Now our answer, this is called the reference angle. That's inside our reference triangle. Our answer is this angle in standard position measured from the positive x-axis out to that terminal ray. So you can think about this in terms of degrees or radians. You're welcome to do the conversion first or second if you'd like. But if this is 30, then that means this is 150, right? 150 plus 30 gives us 180. In terms of fractions, what I would think is that 30 is pi over 6. So I ask myself 1 minus 1/6, that gives me 5/6. Or you can ask yourself what plus 1/6 makes 1 whole, 5/6 plus 1/6 makes 1 whole. In general, this angle, when our terminal ray is in the second quadrant, this angle is always going to be pi minus this reference angle. So our answer here is 5 pi over 6, or if you wanted to look at it at 150 degrees and then do the conversion, you can certainly do it that way as well. All right, any questions on this? Any questions? We will continue to work with inverse trig functions for like 2 more sections in this chapter. So we'll get plenty of practice. If you're not totally comfortable with this yet, we'll get a lot more practice. The next thing I want to do is talk about these cancellation properties of a function and its inverse. Okay, so we talked about this in Math 126 in section 5.2, but I want to refresh your memory on these cancellation properties, and then I'll put it in terms of sine, cosine, and tangent. Okay, so first I have a question for you. And you guys at home, I'd like you to vote too. You can type into chat if you think true or false. Square root of x squared is always equal to x. True or false? What do you guys here think? True or false? How many people think true? How many people think this is always true? How many people think false? I got about half and half. So interesting. How about this? How about square root of x squared is always equal to x? True or false? Do a square and a square root always cancel each other out? What do you guys think? True or false? How many people think true? How many people think false? Oh man, everybody here voted true. This is a big fat false. This is false. This is not true. Okay? Think about some value that this doesn't work for. So anybody, Pick an X value, think about an X value. What number would this not work for? Okay, how about this? What am I not allowed to take a square root of? A negative. So how about this? Is this true? I'll put a question mark here. Is this true? Do the square root and the square cancel each other out? No way. Okay, so this brings up a really important point. A square and a square root, these are inverses of each other. They do the mathematical opposite. However, a function and its inverse do not always cancel each other out. This is not always true. It is not true when we plug in some number here that is not in the domain of the inside function. Okay, if we plugged in any other number, right, if we had square root of positive 5 squared, absolutely no problem. But what happens here is when this number is not in the domain of the inside function, this part is not actually mathematically defined. And since this is not defined, this whole thing can certainly not have an answer. Okay, so this does not work for numbers that are not in the domain. So what this says is if we take a function and its inverse in a row, so we take the composition of a function and its inverse in either order, this equals X only if our input is in the domain of the inside function. So only if we're allowed to plug it in the first place. So here our inside function is f, so only if x is in the domain of f. In the opposite order here, this is true only if x is in the domain of the inside function, which was f inverse. So this is from Math 126 in chapter 5. So we should have already studied this in our last math class, but I wanted to refresh your memory on this. Okay, so what I'm going to do now is I'm going to list it out for sine, cosine, and tangent, and inverse sine, inverse cosine, and inverse tangent. I don't want you to be overwhelmed with how I'm going to list this out, but it is important that I put all this stuff out formally for you. As we go through the examples and we ask ourselves, does sine and inverse sine cancel each other out? We'll talk through yes or no. So you don't necessarily have to memorize this list I'm about to write out for you, but I'll put it down formally just in case you wanted to see it. So inverse sine of x is equal to x, and we'll do sine of inverse sine of x is equal to x. And we want to list out when is this true. So what this is saying is inverse sine and sine essentially cancel each other out, right? We can cancel these out much like a square and a square root. This is only true if x is in the domain of the inside function. Okay, so this inside function was regular sine. We restricted the x values, the domain of regular sine, from negative pi over 2 to positive pi over 2. So I'm going to write this a little bit compactly. This symbol means is an element of, in other words, is inside negative pi over 2 to positive pi over 2. The other way of thinking about this is our output. Inverse sine, the output, the function on the outside has to return something between negative pi over 2 and positive pi over 2. So that's the only time it works. Okay, next one, sine of inverse sine of x, only if x is in the domain of the inside function, which our domain was the range of regular sine, so negative 1 to 1. Again, you do not have to memorize this long list. We'll talk through the problems and show you how to do it. We'll do the same thing for inverse cosine and cosine in both orders. And then we'll do the same thing for tangent and inverse tangent. Okay, so let's fill these in. So in order for these to cancel each other out, like a square root and a square, this input has to be in the domain of our original function. So for cosine here, we restricted the domain from 0 to pi. Here, inverse cosine, the domain was the range of regular cosine, so that was from -1 to 1. Here, this is only true if our input is in the allowed input in the domain here of tangent, which was from -pi/2 to +pi/2, not including the endpoints because it was undefined. Here, inverse tangent of x, our domain for inverse tangent is the range of regular tangent, which was all real numbers. So this should always work. Okay, so again, don't feel like you need to memorize all of this. We'll talk through it as we're going through the examples. I'll talk you through them. All right, let's do some examples now. So let's find the value. First one, let's find inverse cosine of cosine of 8pi/9. Okay, so here's what you want to think about when you're working through these problems. Anytime you see a function in its inverse, so sine and inverse sine, cosine inverse cosine, tangent inverse tangent, or if you find square root square, you should always ask yourself, do these cancel each other out? Okay, so what we want to do is ask ourselves, do these cancel each other out? That would make this problem really easy for us. In order to cancel each other out, what we want to do is look at this inside function. We want to look and make sure that the input is in the domain of the inside function. Okay, so cosine, we restricted the domain. Remember, to quadrant 1 and quadrant 2, that was from 0 to pi. So we ask ourselves, 8pi/9, is that between 0 and pi? What do you guys think? Yes or no? Is 8pi/9, is that between 0 and pi? Yes, okay. 8/9 is between 0 and 1. So yes, this is between 0 and 1 pi. So that means those cancel each other out. And we get that this is 8pi/9. This is true. You don't have to write this rationale on your homework, but this is true because 8pi/9 is an element of 0 to pi. It's between 0 and pi. It's in the first or the second quadrant. If you couldn't visualize that, you could always draw a picture, right? 8pi/9 looks like that. Yeah, it's between 0 and pi. It's in quadrant 1 or quadrant 2. Good to go. Any questions on that? Let's do some more. How about sine of inverse sine of 1/5? Okay, so now our inside function here is inverse sine. So what we want to ask ourselves is this input, this 1/5, is it in the domain of inverse sine? So remember, our domain of inverse sine corresponded to our range of regular sine. So regular sine, that sine graph that we saw last chapter, our range, the y values that we hit was from -1 to +1. That means our domain here, what we're allowed to put in, is between -1 and 1. So what do you guys think? 1/5, is this between -1 and 1? Yes or no? Yeah. So do these cancel each other out? Yeah. So whoop, whoop, and we just get 1/5. Okay, so this is true, and again, you don't have to write the rationale, but if you'd like to see this, this is true because 1/5 is in the domain of inverse sine, which is -1 to 1. Cool. Let's do some more. How about inverse tangent of tangent of negative 3 pi over 13. Okay, this one's a little bit harder to see, but what you want to do is think about this in terms of fractions. So we look at the inside function first, and we ask ourselves, is this input in the domain for the inside function? So tangent, remember we restricted our domain of tangent from negative pi over 2 to positive pi over 2. We want to ask ourselves, is negative 3/13 in this interval? Okay, so if you wanted to actually do the division, you could divide this out. But what we want to make sure is that 3/13, negative 3/13 is between negative 1/2 and positive 1/2. So yeah, 3/13, negative 3/13 is in between this. If you wanted to draw a picture, we're trying to make sure this is in 1 or 2. Negative 3/13 is going to be somewhere like that. So yeah, no problem. In terms of fractions, you can think negative 3/13 is between negative 1/2 and positive 1/2. So sure. So we get negative 3 pi over 13. And this is true because negative 3 pi over 13 is in that interval. I got 4 more for you guys, and this is where they kind of start to get a little bit more interesting. Anybody need more time on this page? Question?
Why is it not
Okay, so for tangent, remember when we had this picture of tangent, when we figured out what the domain had to be, because tangent is actually undefined at these endpoints, we can't include them in our endpoints, so we actually put parentheses here. So the question was, why parentheses and not brackets? And that's because when we originally defined inverse tangent, it was based on this picture. Tangent is not defined at these endpoints, so we have parentheses here and not brackets, and we just carry that through to all the rest of our problems. Any other questions? Okay, what did I say? I have 4 more examples for you guys. Let's do some more. And these ones where it starts to get a little bit exciting. Okay, next one, cosine of inverse cosine of 1.5. So anytime you see sine, inverse sine, cosine, inverse cosine, tangent, inverse tangent in a row, you should always start by asking yourself, do they cancel each other out? In order to cancel each other out, this value on the inside has to be in the allowed domain of the inside function. Okay, so inverse cosine, the domain for inverse cosine corresponds to the range of regular cosine. Okay, so let's think about our cosine graph, that wave graph. Our range, the y values cosine hits, is from -1 to 1. That tells us the range here corresponds to this domain, so this value has to be between -1 and 1. So is 1.5 between -1 and +1? Yes or no? No. So do these cancel out? No. So the question is, what is our answer? We have to decide, is there no solution, or do we have an answer and it just happens to not be 1.5? Okay, so we need to decide, is there a solution or is this no solution? So let's start by looking at the inside operation. Anytime we have a composition of functions, meaning 2 functions applied in a row, we always start on the inside first. Okay, so inverse cosine says find the angle in 0 to pi whose cosine is 1.5. So can we find an angle whose cosine is 1.5? What do you guys think? Yes or no? Think about that graph of cosine. What's the maximum y value we will ever get on cosine? 1. Can we ever find an angle whose cosine is 1.5? No way. So this has no solution. No solution, and that's because it is impossible. We can't find an angle with cosine of 1.5, okay? So when it's mathematically impossible, we're gonna have no solution. Let's look at a couple more examples and see where we might find some other outcomes. So next one, sine of inverse sine of -2. Okay, so again, anytime we see sine, inverse sine, cosine, inverse, tangent, tangent, we should always ask ourselves, do they cancel out? In order to cancel out, we look at the inside operation and find out, is this input in the domain? Okay, so inverse sine, our domain, much like inverse cosine, is -1 to 1. Is -2 in between -1 and 1? No, so they don't cancel out. Okay, so the next thing we have to ask ourselves is, does this make sense? Can we find an angle? So inverse sine of -2, this asks us to find an angle whose sine is -2. Okay, so again, think about that sine graph, that wave we saw in the last chapter. What is the lowest possible y value we will ever get? -1. So is it possible to find an angle whose sine is -2? No way. So again, we have no solution. And that's because we cannot find an angle with sine of -2. All right, maybe you guys are starting to get the hang of this. Let's try this next one. How about tangent of inverse tangent of 9? Don't shout out the answer yet. I want you to think about this for one quick second. Maybe you guys at home watching, maybe you can think about what this is, and if you know the answer, type it into the chat box. What do you guys think? Tangent of inverse tangent of 9. What do you guys think this is equal to? Oh, I didn't get you. This is equal to 9. Okay, so be careful here. Up here we had no solution, no solution. Here we got 9. So what's the difference? In order for these to cancel each other out, this number has to be in the domain of the inside function. The domain of inverse tangent corresponds to the range of regular tangent. So if we think about our graph of tangent, the range, the y values we actually hit is all real numbers. So this will always work. Good to go. Our answer is 9. Up here we got no solution because we can't find an angle with sine or cosine outside of -1, 1. Here we can find an angle whose tangent is 9, right? It would be something up here. No problem. All right, now I got a really tricky one for you guys. How about inverse sine of 8 pi over 7? Okay, the first question we should ask ourselves is, do the inverse sine and sine cancel each other out? In order to cancel each other out, this number has to be in the restriction for the inside function, has to be in the domain. We restricted the domain of sine to negative pi over 2 to positive pi over 2, which was quadrant 1 and quadrant 4. Now you can think about this in terms of fractions, or if you want to draw it out, you can certainly draw it out. 8/7 is 1 1/7. So 8 pi over 7 looks something like this. Oops, 8 pi over 7. That is certainly not in between negative pi over 2 and positive pi over 2. It's not in quadrant 1 or quadrant 4. Okay, so first question is, do they cancel each other out? And the answer is going to be no. The next question is, did we get no solution or do we have a solution? Okay, so in order to have no solution, as we did up here, this inside part, the inside function, made no mathematical sense. So let's take a look at this one and let's evaluate if the inside makes sense or not. Sine of 8 pi over 7. Okay, so what we did in chapter 6, all we did was find sine, cosine, and tangent of an angle. So sine of 8 pi over 7, does this make sense? Sure. We could draw 8 pi over 7. We could drop a perpendicular, forming a triangle. We could figure out what the opposite and hypotenuse was, and we could answer this question. So does this make sense? Yes. Mathematically, sure, we can figure this out. We'll get some number between -1 and 1. Then inverse sine of some number between -1 and 1 would tell us to find an angle in this range whose sine is that value. Does that make sense? Yes. Okay, so on this one, we can find a solution. It just happens to not be 8 pi over 7. Okay, so we have to take a different approach to this. So we can find a solution, it just happens to not be 8 pi over 7. So I think this is a good place to stop. I will show you guys next lecture how to find the value. Okay, so find the value. So inverse sine of 8 pi over 7. Okay, so the first question is, anytime we see inverse sine and sine, or inverse cosine and cosine, or inverse tangent and tangent in a row, the first thing we should ask ourselves is, do those cancel each other out? And as we saw yesterday, in order to cancel each other out, our input has to be in the domain of the inside function. Well, our domain of this inside function here is negative pi over 2 to positive pi over 2. Okay, so 8 pi over 7 is not in that domain, as we talked about last class. So these are not going to cancel each other out. The next thing we'd want to consider is if there is no solution. So if this is mathematical gibberish, and then we would have no solution. Okay, so we look at the inside operation first, which is sine of 8 pi over 7. Mathematically, that makes sense. And then inverse sine of some number between -1 and 1. Mathematically, that makes sense. So yes, we can find a solution. It just happens to not be 8 pi over 7. Okay, so what we want to do is figure out how do you find this value, how do you evaluate this? So what we want to do, let's look at this outside operation. We have inverse sine. From last class, remember, anytime we have inverse sine, inverse cosine, or inverse tangent, we should think we need to find the angle. Okay, so this inverse sine is telling us we need to find the angle. What do we know about that angle? We know, I'm trying to figure out why this is still auto-focusing. Maybe it just takes a couple times. Okay. I'll play with this later and see if I can find a solution to this. Okay, so on this outside here, we're asked to find the angle. And what do we know about this angle? We need to find the angle for inverse sine. It has to be between negative pi over 2 and positive pi over 2, whose sine is whatever is inside the inverse sine, right? So we want to find the angle in negative pi over 2 to positive pi over 2, whose sine is whatever this value is. Now, so let's draw a picture of 8 pi over 7 and talk about what sine of 8 pi over 7 might look like. Okay, so thinking about this in terms of fractions, 8 pi over 7, 8 divided by 7 is 1 and 1/7. So here's 1 pi. So 8 pi over 7 is going to be somewhere over here in the third quadrant. Now, we only know how to do a 45, 45, 90 triangle and a 30, 60, 90 triangle. So this is obviously one that we're not going to be able to actually find the value for by hand. But our process would still be the same, right? We would still drop a perpendicular forming a triangle. We would still figure out what this reference angle is, and then we'd evaluate from there. So this entire angle here is 8 pi over 7. We know that to 180 is 1 whole pi.
So in terms of fractions, 8/7 is 1 1/7. So here's 1 pi, plus this is going to be 1/7 pi. So this angle is pi over 7. Okay, so we're asked to find the angle in negative pi over 2 to positive pi over 2 whose sine is whatever the sine of this angle is going to be. Now looking at this triangle, we don't know how to do that. So we'll just say whose sine is the same as 8 pi over 7. Okay, we don't actually have a value for this, but if we used a calculator, we could get some answer between -1 and 1. Okay, so what I want to do is draw a matching triangle. I want to find an angle whose sine is the same as this angle. Okay, so all I have to do is draw a matching triangle. So we want to find the angle in between negative pi over 2 and positive pi over 2. So that's going to be in quadrant 1 or quadrant 4. The way we determine what quadrant that angle goes in is based on the input value being negative or positive, right? If we're positive, we're in the first quadrant. If we're negative, we're in the fourth quadrant. So we want to find an angle whose sine is the same as this angle. So the first thing we need to do is ask ourselves, sine of 8 pi over 7. Here's our picture. So in the chat box over there, I want you to tell me sine of 8 pi over 7, sine in the third quadrant here, should be what? Positive or negative? Go ahead and type it into the chat for me. Positive or negative, sine in this quadrant? Negative, 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 great. Yes, so remember all students take calculus, so we have a T, which means sine is negative. Okay, so if sine is negative in this quadrant, what we want to do is put a matching triangle in quadrant 1 or quadrant 4, and we want sine to also be negative. So is sine negative, again in the chat box here, tell me where I should draw the angle. Sine is negative in what? Quadrant 1 or quadrant 4? Which one? Go ahead and type it in. Great, quadrant 4, nailed it. So what we're going to do is draw a matching triangle. So here is pi over 7. Now, isn't it true that regardless of knowing or not knowing these sides, that sine of this angle and sine of this angle should be exactly the same thing, right? Those triangles match. So theoretically, or not theoretically, it is true that sine of this angle and sine of this angle will have the same value, and sine here is negative and sine here is also negative. So we're going to get the same outputs. So our goal was to find an angle in negative pi over 2 to positive pi over 2 whose sine is the same as this angle, and we did it. The hard part here is to remember that anytime we're doing these inverse trig function problems and our angle is in quadrant 4, we always are measuring this angle in standard position, and moving around, this should be a negative angle. So our final answer here is negative pi over 7. We'll do 2 more of this type. And again, all we're doing is kind of coming up with these matching triangles. Any questions on this problem? Okay, let's do 1 more. 2 more, I got 2 more for you. So let's find the value of inverse sine of 5 pi over 8. So the first thing we should do anytime we see sine and inverse sine in a row, we should ask ourselves, do they cancel each other out? In order to cancel each other out, this input has to be in the domain of the inside function. So the domain of sine, our restricted domain, was from negative pi over 2 to positive pi over 2. So remember, pi over 2 is 1/2 pi. And so what we want to evaluate is 5/8 greater than or less than 1/2. Well, 5/8, that's more than 1/2, so it's actually outside of that domain. So these don't cancel each other out. The next thing we should ask ourselves is, do we get a solution? Does this make sense mathematically, or is it gibberish? Well, it turns out sine of 5 pi over 8, even though you and I don't know how to evaluate this by hand, a calculator can certainly do that. So yes, that makes sense. We get some number between -1 and 1. And then inverse sine of some number between -1 and 1, absolutely, we can evaluate that. Okay, so yes, this makes sense. So yes, we can get an answer. It just happens that the answer isn't 5 pi over 8. And the reason why it can't be 5 pi over 8 is because inverse sine, if we put equals 5 pi over 8 here, inverse sine can never return something that's greater than pi over 2. Okay, so that's not possible. Okay, so yes, we can get an answer. We just have to figure out what it is. Okay, so anytime we see inverse sine, inverse cosine, inverse tangent, we should think we need to find the angle. And the angle has to be in our restriction, which for sine was negative pi over 2 to positive pi over 2, whose sine is whatever's in here. Now, even though we don't know this value, all we're going to do is find the angle whose sine is the same as 5 pi over 8, right? Usually we'd find the angle whose sine is what's in here, and what's in here is, we're just going to say the same as 5 pi over 8. Okay, so first up, let's look at 5 pi over 8. Let's draw a picture. Okay, so 5/8, that's a little bit bigger than 1/2, so I'm going to put it right here. Drop a perpendicular, forming a triangle. Now, if this is pi, we ask ourselves pi plus what gives us 5 pi over 8, or pi minus 5 pi over 8. However we want to look at that, this is going to be 3 pi over 8. Okay, so in the second quadrant, this reference angle is always pi minus our angle. So pi minus 5/8 gives us 3/8 pi. Okay, so again, this is a triangle we don't know how to evaluate by hand. That's not a problem. We can still solve this problem. Okay, so what we want to do is find an angle in negative pi over 2 to positive pi over 2, whose sine is the same as this triangle. So let's draw it. What we want to do, we know our angle has to be in quadrant 1 or quadrant 4. So the way we determine what quadrant the angle is in is based on if our input is positive or negative, if we're trying to find inverse sine of a positive or negative number. Okay, so let's go back to the angle we're trying to match. So over here we have an angle in the second quadrant. So in the chat box there, you guys tell me, sine in the second quadrant is what? Positive or negative? Positive, positive, perfect, right? All students take calculus, sine in the second quadrant, positive. Great. Okay, so if sine is positive, what I want to do is put an angle in either quadrant 1 or quadrant 4 where sine is also positive. So what quadrant should I draw my angle in? Quadrant 1 or quadrant 4? Quadrant 1, quadrant 1, quadrant 1, great. So my drawing is not to scale at all. I did a terrible job here, but these are matching triangles. So if this angle is 3 pi over 8, this angle is 3 pi over 8. Our answer is this angle in standard position, which is just 3 pi over 8. Now you might start to notice some patterns. I have students every semester that tell me, oh, if we're in the second quadrant, then my answer is just pi minus this. If we're in the fourth quadrant, then my answer is pi plus this. Okay, you might see some patterns emerge. I would encourage you guys to always draw out the pictures. And while you might see some patterns, you can use those as a self-check when you're doing the homework. But I wouldn't totally rely on those because you're gonna have to memorize a bunch of stuff. So it's much easier just to draw the pictures. Let's do one more. Any questions on this one? Okay, so find the value of inverse cosine of negative pi over 5. Okay, so again, anytime we see sine and cosine in a row, or inverse sine, inverse, sine and inverse sine, cosine, inverse cosine, tangent, inverse tangent. Anytime we see those two things in a row, we should ask ourselves, do they cancel each other out? Okay, in order to cancel each other out, we need this value in here to be in the domain of the inside function. So cosine, we restricted our domain from 0 to pi. negative pi over 5, that's negative, that's less than 0, so it's not in the domain. Okay, so first of all, they don't cancel each other out. The next thing we should ask ourselves is, can we get an answer? And in order to get an answer, we need to make sure it makes mathematical sense. So can we evaluate cosine of negative pi over 5? Yes. Can we evaluate inverse cosine of some number between negative 1 and 1? Yes. All right, so we can get an answer. It just happens to not be negative pi over 5, and that's because, of course, inverse cosine cannot output a negative. So here, inverse cosine asks us to find the angle in our restriction for inverse cosine, which is 0 to pi, whose cosine is, and then we just have here, cosine has to be the same as cosine of negative pi over 5. Okay, so let's draw a picture. First, we'll start with cosine of negative pi over 5. So measuring in the negative direction, negative pi over 5 looks something like this. Here, my reference angle, I'm going to list it as pi over 5. We know this is negative because we're going in the negative direction. All right, now our goal is we want to find an angle in between 0 and pi whose cosine is the same as this angle. So let's draw our picture from 0 to pi. So that means we need to find an angle in quadrant 1 or quadrant 2. Okay, so the last couple of examples, I broke this down into 2 steps. This time we'll just do it in 1 step. So the way we determine what quadrant our angle goes in, quadrant 1 or quadrant 2, is based on our input being positive or negative. So we want it to match cosine of this angle. What do you guys think? Should I draw my angle in quadrant 1 or quadrant 2? Go ahead, type it into the chat there. 1, 1, 1, great. Yes, so cosine in the 4th quadrant is positive, so that means we want to put this angle in the 1st quadrant. So matching triangle, this is pi over 5. Our answer is this angle in standard position, which is just pi over 5.